Yes, good morning. In my presentation, I'm going to first tell about a couple of definitions related to the topic, so about smart buildings and building operation and maintenance. Then I'm going to tell about machine learning into application areas in building control and fault detection and diagnostics. And I look at the topic from two perspectives as I work in two places. So from Aalto University, I will tell about the research side, and more like practical implementations from the ground side. But starting from the definition of smart buildings, you can find several definitions. There's no standard one, but many times these kind of topics come up when we talk about smart buildings. So it's about the healthy indoor environment. We spend 90% of our time indoors, so it's really important to us, the healthy indoor environment. It has an effect on our productivity as well. Then it's the energy efficiency, energy flexibility, examples like Risto told in the previous presentation. Buildings consume 40% of all energy, so really important part as well. Third topic is more like a convenience, how smart buildings can help us in everyday life. For example, when you come to the office, how can you find your free parking spaces, free meeting rooms, free work desks, or the services in the building. Then I would say that smart buildings, they should learn based on measured data and feedback. So at the moment, buildings are stupid in that sense that we only design the functionalities and controls beforehand, and these functionalities stay the same over time during the whole life cycle of the buildings. But smart buildings, they should learn based on data and become smarter over time. Then many building owners are looking for future-proof buildings. Since the life cycle of the building is really long, 50 to 100 years, how could we make sure today that the building is also like smart in the future, let's say in 10 years or 20 years? And I would say that at minimum it means that there should be the building service system should have open interfaces so that we can utilize the data in designing the smart services in the building. Previously, we didn't have any like a rating system to tell is the building smart or not. At the moment, there exist several ones. One is the smart readiness indicator that came from the EU Commission. There are also other ones, for example, smart building certification and smart score that also look perhaps a bit wider the topic of smart buildings. So it also includes like connectivity, cybersecurity, and these kind of like applications that help in the everyday life of the building users. Then a couple of words of the building operation and maintenance. So building industry is a really significant industry. It's the world's largest asset class, worth at something like 380 trillion US dollars, 3 times larger than the stock markets, for example. Then as I said earlier, that buildings use 40% of all energy, really important from the environmental perspective. And as we spend the 90% of our time indoors, the healthy indoor environment is really important to us as well. So building industry being really significant, but when we come to the building operation and maintenance, there's a quite huge mismatch at that moment. You could say that it's the Cinderella of the vinyl industry. Many times seen really like unproductive. The workers have low wages and is many times under budget cuts. So instead of being like a significant industry, you don't see that many investments on the building operation and maintenance. Although especially the operations, like the efficient use of devices, is really important from the energy usage point of view. So it has a really big impact on the energy usage. So on that area, I will concentrate then more how to use machine learning in the building operations and in the two areas of building control and fault detection and diagnostics. Before going to machine learning methods, a couple of words on the traditional control methods. The typical ones that we use today are the on-off control and PI control. And here's an example from an office building where you can see on the x-axis is the time and y-axis the utilization rate in the office building. And time schedules, one format of the on-off control, for example, used in the ventilation. We turn on the ventilation a bit before the first users come to the office. Then we can use presence control, for example, in lighting systems or adjusting the temperatures in the spaces. And then PI control, for example, the demand-based ventilation. So using the CO2 or temperature measurements, we can control the ventilation and provide the air rate to the spaces that have users. So we can quite a lot save energy already using these methods, but where they have challenges is multi-objective optimization in situations where we have several inputs, several outputs that we want to control, and also if we want to utilize predictions. So typically, these traditional control methods only can look at the present time, but with machine learning, we can look to the future as well. So I've divided the building control solutions through 3 levels, starting from the sensor level, where we can utilize the machine learning in calculating estimations and predictions. One area is there to estimate the amount of people in the room, and for that purpose we can use different kind of technologies. For example, Wi-Fi, Bluetooth. That like typically we have the Wi-Fi already in the building. We can utilize that to make estimates of the amount of people, and you can get like a rough estimates, perhaps not in the space level, but some estimates of the amount of people. If you want more accurate information of how many persons there are in the room, you can use cameras, but then they have like privacy issues. A fourth option could be to use environment sensors like CO2, temperature, VOC sensors, and of those we can also calculate like some rough estimates, like there's like a small amount of people in the room or a large amount of people in the room. And when we talk about machine learning, of course, one option is to use data fusion. So combine different kind of measurements and based on those, make the calculations. Then predictions we can use in the indoor environment side and also predicting the energy usage. It's either in the building level or in the sub-metering level. So really many use cases there. Here's one example of our study in Aalto that we compared different kind of machine learning methods in estimating the amount of people in a meeting room. So we had several sensors that we used there, like a people counting camera, passive infrared sensors, then different kind of like indoor environment sensors, and compared different kind of machine learning methods there. And as you can see from the table, that the most accurate one was KNN, so K nearest neighbor method, and we could like close to 100% calculate the presence information in the room. There are still like situations where you could be in a room that the sensors that don't notice you, or in some cases when like people come and go to the room, we cannot calculate all the people, but like really well, almost 100%. And when it comes to the calculating the exact amount of people in the room, we are something like 80%. And especially there, if there's like really many people in the room, for example, the cameras cannot detect all the persons in the room. Then we could use also humans as sensors. So, for example, with this kind of wristband, as here on the figure on the left-hand side, we can measure our pulse and our skin temperature and our galvanic skin response. And with machine learning, we can find correlations between those measurements and our thermal comfort. And you could say that perhaps in the future we could provide more personalized environments for our building users. At the moment, we all have the same temperature, for example, at the office, but with these kind of technologies here on the right-hand side, we could also provide more localized and more personalized environments for our building users. Then the other area of machine learning in controls is the room and system level. And that is typically used in the multi-objective optimization. For example, integrated room solutions where we have the shading, lighting and cooling system, and doing then optimization between the cost, energy costs, and the good indoor environment. So, okay, we would like to get some daylight in, but not too much so that the cooling costs don't rise. And then again, other application area is like the system level optimization. Is it then ventilation, heating, cooling, or lighting systems? And they're like optimizing the energy usage or the peak power or the good indoor conditions. Here's an example of using an demand response in the room heating. Quite similar example that Risto had. So here you can see the time of the day again on the x-axis, and on the y-axis you can see the heating valve position and the electricity price. The electricity price is this yellow line, and you can see that we have heated up the room a bit before the price peak, and by that saving costs. And for like a machine learning algorithm, it takes a while to learn the thermal dynamics of the room and how much before you should heat up the room to avoid the price peaks. Then the third level of the building controls is the building level, where things come even more complex than on the room level. There we can like combine the optimization to different building systems. Is it then HVAC, lighting, plus then energy storage, on-site production, or even electric cars. So things start to become quite complex, and in that sense, there's a good opportunity for machine learning solutions. You could also use like rule-based systems, but they could become quite complex to update and maintain. And in that sense, machine learning is quite useful in this area. And especially when we combine the demand response. And there are like several markets that you can use in the demand response. For example, in Finland, first the peak power of the electricity, then the hourly price, and then we have 8 different markets for the reserve markets. So like depending on how fast you can react from like milliseconds to 15 minutes. So there are really different markets in the reserve market side. Plus, if we can also like optimize when to use electricity for heating and when to use district heating, as Risto had in his presentation. They are also looking at the peak price and these kind of like a seasonal prices that we are in Finland. So really many objectives for the optimization there. And why to end on the building level, as we can also optimize on the neighborhood level or on the block level and utilize the waste heat from some of the buildings. Let's say if there's a cooling system and we can utilize the waste heat from that building to other buildings as well. And this is, of course, a really interesting like a topic for research, since a lot of like opportunities to do optimization here. what I've noticed lately that reinforcement learning is coming more common, at least in the research side of one of the machine learning methods. What's good in reinforcement learning is that it learns over time. So it's here's the principles of the reinforcement learning. It's quite close to the concept of feedback control in the automation system, where we have the agent that does actions to the environment. Let's say it's in a ventilation system. And then we get the state information from the environment. It could be like a CO2, temperature information from the environment. And the agent then learns the correlation between the outputs and inputs. And with the reward system, it learns over time and it gets better. And the reward could be something like related to cost of the energy or the good indoor environment. And what is also good in the reinforcement learning that it learns to the changes of the environment. So let's say that the space size changes over time, and the agent then can learn the new correlation between the outputs and the inputs. Now, how can we then in the future manage all these machine learning models if we're going to have tens of them in our buildings? We're going to have them in the sensor level, room level, in the systems, in the building level, like really many different machine learning methods. And especially in buildings that all are unique. They have the different size, different shape, different thermodynamics of the building. There are different combinations of technical devices in the buildings. So we are going to have unique machine learning models in each building. It's quite difficult to like copy the machine learning models from one building to other, since the environment is totally different. So besides that the buildings are different, we are going to see changes in the environment of the machine learning methods. There are going to be like changes in the tenants. We are going to have renovations during the life cycle of the building. Perhaps the building uses will change over time. So really many like complex issues that will have an effect on the machine learning methods. And if this is the case for just one building, how about if we have a building owner that have hundreds of buildings? How do we manage this? And I would say that we need machine learning operation in a similar way that we have building operation. We need the tools and processes to operate the machine learning methods. Typically, research concentrates here on the first steps of the machine MLOps. So here on the data engineering, model engineering, model validation, verification. But in the practical world, there are several other steps that we need to take into consideration. So it's the release of the first version of the machine learning method, then deploying it, operating the model in the building. You need some kind of like infrastructure to operate the models. Then you need to monitor the models, the performance of the models, to see that are they performing as they should. And if there are changes in the building, you need to retrain the models, perhaps do some changes to the models, and then again test the model and release the new version of the model, and so on. So we go into circles. Yes, then to the other topic of the application area of the machine learning models, and it's for detection and diagnostics. Detection meaning that we can detect the anomalies in the data set, and diagnostics meaning that we can find the causes for the faults. It's not a new topic in the research world. The studies start from the 80s, and you can like divide the approaches into 3 different categories. So it's model-based methods that are like based on mathematical models of the environment. Then are these knowledge-based methods example here on the right-hand side is kind of like expert rules in a format of like if then else rules. Example of like a ventilation system where we have first checking that, okay, is the temperature after heating coil larger than the temperature before the heating coil? If it's yes, is the heating valve closed? And if yes, we can say that there's a valve leakage in the heating coil. The third approach is data-driven, and these meaning these machine learning methods. Now here's an example how we have utilized knowledge-based methods in Granlund. This is a system where we transform the measurements into 0 to 100 KPIs, performance indicators. And the idea is that we have like a certain target limits for the measurements. As here on the left-hand side, you can see the targets for temperature in a certain room. These are the target temperatures, and we calculate the time where the actual measurements is between the target values. And here you can see that, okay, in the beginning the temperature is quite well in between the target values, but it then drops during the day, and this is the performance indicator value. As the temperature drops below the target limit, it drops to 0 here. The idea is to, by calculating this, okay, how much of the time we are between the limits, calculate the 0 to 100 performance indicator for each room, for each device, and calculate it for 1 day, 1 month, or 1 year. And by that, the building expert can notice that, okay, which rooms have problems with temperature, or CO2, or VOC values, or which building systems have problems with energy performance. So in that size, we can also have some target limits. Let's say that, for example, on heat recovery efficiency should be always more than 60%. And idea of having then one single figure for the whole building, or even for a whole building portfolio, that tells how it's like performing in average. And we can then see some history information of the past 12 months. And what is important for the building expert is to see that, okay, which rooms or which devices are performing the worst. And you can concentrate your time here for those and trying to find the reasons behind the poor performance. So the expert time doesn't go in finding the faults in the buildings. You can concentrate on finding the causes of the poor performance. If the previous example was more like a bottom-up approach for FDD, meaning that we started from the room and device level and went up to the building level, we use machine learning in like a top-down approach. So we first look at the building level energy consumption and then go down to the sub-metering level. And we use machine learning in making predictions for the energy usage and compare the actual energy usage to these predictions, and especially look for this kind of like an repeating anomalies in the data. Okay, we are also interested in these like high anomalies on a daily level, but especially interested on the repeating anomalies. So there might be situations in one day that, for example, the maintenance man changed the time schedule of the ventilation because there was like some event in the building, and it should be running more, and therefore the consumption was higher. And then it's like, okay, but we are especially then interested in these repeating ones, since if it's like every Monday there's a bigger consumption than it was previously, perhaps there's actually something wrong in the building service systems. At the moment, it takes quite a lot of time to set up the fault detection and diagnostic systems. And much of the time goes to that to understand the measurements in the building. So I would say that there are as many different kind of methods to describe the data as there are buildings. It depends on the engineering company that has designed the building service systems, or the contractor that have programmed the automation system and so on. So really many ways of describing the data in the building. And in that sense, ontologies that are like a common way of describing the data would help a lot. There are some ontologies that are already used in the market, like haystack or brick, and there's like also research going on that field. One of the ideas that we have in Aalto is FSO ontology, so flow systems ontology, that describe ventilation systems, heating systems, and cooling systems. And where it is really good is it describes the energy flows in the system. So here you can see an air handling unit, like a common devices for you, the damper, supply filter, and then heat recovery, heating coil, and so on. And with the FSO, we can describe the relationship of the devices and measurements, and also the relationship between the systems. So here from the heating coil, we come to the heating system as well. So for example, if there's some fault in the heating coil, it might be that the heating coil has some problems, but actually the cause of the problem might be here on the heating system side, not in the ventilation system. And with this kind of like ontologies, we could do like a deeper analysis on the performance of the systems. As in a similar way was in the MLOps side, I would say that in the FDD side, the research concentrates only on the first steps of the process in the practical world. And like here in FDD, it's quite much above detecting the anomalies in the data. But after that, you need to diagnose the cause of the anomaly. And it could be quite easy to find the reason for that, just checking the building automation system, or it might need some expert to go on site and to like a more detailed reasoning of the problem. And when we have found the fault, we should do like a cost-benefit analysis to evaluate that what should we do, and how much does it cost, and what are the benefits of fixing the problem. And it might be so that if the benefits are low, or for example the fault is somehow related to like a repair or an investment, it might take a while to fix the problem in the building, and it would take from like days to years even that the problem is then fixed. So then we fix the problem, and what is quite often then forgotten is the verification that, okay, when we did the repair, did we fix the problem, and did we get the benefits that we calculated in the evaluation phase? And that we should do as well, to make sure that the system is then performing better, and it gets the savings as promised. That was my last slide. If you want more information, you can find our Aalto University Research Group website from here, where you can find information on our research. So it's on ontologies, on advanced control methods, workplace applications, and lighting, and different kind of smart building rating systems. And then again, on the ground side, our innovation projects are here, more related to AI, digital twins, and smart energy systems. Thank you for attention.
Thank you very much.